Chemical reactions, part 2. The 5 types of reactions, as well as identifying the type of reaction if you know the chemical equation. We'll be using a few different reference sheets. On this ion reference sheet, you can see that for the representative elements, the charges for the common ions are identified at the top of each column. For the 7 diatomic elements, they're identified with that light gray shading. These are elements that naturally form 2 atom molecules while in their element form. We also have several different negative polyatomic ion formulas, a couple of positive polyatomic ion formulas, and some other positive monatomic ions that would be unexpected for some of the representative elements or from the transition metal part of the table where they would have to be determined by experiment. We'll also be using the metal and the non-metal activity series that's on the back of this sheet. We'll be focusing for the most part on this reference sheet, predicting products in chemical reactions, or we'll just call it the reaction sheet for short. Let's start with the first of the 5 types of reactions, combination or synthesis. And I prefer to call this reaction type synthesis because combination sounds a little bit too much like combustion, which is the 5th reaction type. So this comes in 2 varieties: simple synthesis, where we have 2 elements that combine to form a compound, and then complex synthesis. But let's start out with simple synthesis. Here's an example of 2 elements forming a compound. Iron, Fe, combining with oxygen, which is one of the 7 diatomic elements. Again, you can see that it's identified as a diatomic element here because it's shaded in gray. And you might remember the rule of 7. Go to element number 7, nitrogen, make the shape of a 7, and that's 1, 2, 3, 4, 5, 6 elements. Add hydrogen, and that's the 7 diatomic elements. So oxygen automatically has a 2 subscript in its element form. We're going to form a compound, and when we do that, we typically put the metal first, and that'll be a positive ion, and then the nonmetal second, and that would be a negative ion. Now, iron has more than one possible ion charge. If we look on the ion sheet, iron could be 2+ or 3+. So for the sake of having consistent answers, we're told in this problem that we should use iron 3 in the problem. Roman numeral 3 is telling us that we should use iron 3+. Crisscross the 3 and the 2, and we get Fe2O3 for a formula. And you can't reduce a 2:3 ratio, so that's it. That's our answer. Now you might say, well, why didn't we use iron 2+? And that's a great question. Iron 3 is only provided in this problem for a consistent answer from one person to the next. In reality, there might be some iron 2 oxide that's also being produced. We wouldn't really know unless we go into the lab, run this reaction, collect some of the product, and analyze it, and see if the formula matches iron 2 oxide or iron 3 oxide. They do have different mass, so we can tell the difference. Here's another example. Sodium combines with chlorine, which is also a diatomic element. Again, in this simple synthesis, an element and an element forms a compound. So we take the sodium, which is a 1+ ion, and combine it with chloride, which is a 1- ion. Now, many of these monatomic ion charges can be determined, like sodium in the 1+ column and chloride in the 1- column, by just looking at the periodic table. When we crisscross Na1+ and Cl1-, we get a compound NaCl. Again, that's our prediction for what the compound is likely to be. To be sure of that, we'd have to go into the lab and collect that and test it and see if it matches the properties of NaCl. In our third example, we have carbon, C, combining with oxygen, which is again a diatomic element. And it tells us in this problem to use carbon 4 in the product. That means C4+. When we crisscross C4+ and O, which is in the 2- column, we end up with initially C2O4, and we can reduce that 2:4 ratio down to a 1:2 ratio. We get CO2, carbon dioxide. So that's simple synthesis. If we look at the reaction sheet, complex synthesis is the other type, or complicated synthesis. This is where we have a compound and a compound form a new compound. Now, there are 3 recipes, if you want to call them that have been discovered, and they're cataloged here on the sheet. Like any recipe book, this is not all-inclusive by any means. If you were to run a reaction and wonder what the product might be, you could look in a reference book, or you could Google it for that matter, and it's likely that someone has tried that reaction and recorded what the product was. These are 3 common reactions, and I like to refer to them as recipes because that's how we cook, right? We open a cookbook and we look up a recipe and we follow that recipe, and when we put the correct ingredients in, we get the product that we expect. So these are just 3 common recipes for reactions that are complicated or complex synthesis reactions. If you combine water and a metal oxide, you get a metal hydroxide. If you combine water and a non-metal oxide, you get an acid. And if you combine a metal oxide and carbon dioxide, you get a metal carbonate. Let's look at those examples in more detail. Here's the first one. Water and a metal oxide forms a metal hydroxide. HOH is a better way to write water when we're writing chemical reactions. You can write water as H2O, and that's not incorrect, but it turns out that when water is broken apart into ions, it breaks apart into the H1 plus and OH1 minus ion, the hydrogen and the hydroxide ion. So writing it as HOH makes it a little bit easier sometimes to treat it in reactions as H1 plus and OH1 minus. All right, so when these combine, water and our metal oxide here is sodium oxide. Notice that sodium is a metal. Remember that metals are the elements that come from the left-hand side of the periodic table, left of the zigzag line, and sodium's way over here on the left. It's in the 1 plus column. And it's combining with oxide, which is O in the 2 minus column. We crisscross that 1 and 2 and we get Na2O1, or just Na2O. We typically don't write a 1 subscript. And then we use that same metal, sodium, in the product side, and we're going to combine it with the hydroxide ion. The hydroxide ion is on the ion sheet. It's right here. It's a polyatomic ion. And we put a star by that because it's typically mixed in with ites and ates that are normally the suffixes that we see with polyatomic negative ions. It's a little bit of an oddball that is called hydroxide with an IDE ending. Cyanide's the same way. Kind of exceptions to that ite and ate grouping that we see there. All right, so when we combine sodium with hydroxide, we get NaOH. 1 and 1 crisscross, and we don't write those 1s in the subscript position. Now I put this 2 here to balance this equation to make the point that sometimes these equations are not balanced. Notice we have 2 H's on the left, and then if we put a 2 there, that would make 2 H's on the right, 2 Na's on the left, and 2 Na's on the right, 1 O on the left, actually 2 O's on the left, and 2 O's on the right. So if we didn't put that 2 coefficient, that would not be a balanced equation. And that's okay. We're not going to balance these equations. That's something that is probably best done as a separate operation. Right now we're going to focus on identifying the different reaction types. All right, the second type of complicated synthesis or complex synthesis is where a compound and a compound forms a compound with water and non-metal oxide as our 2 compounds on the left, and acid as our compound on the right. So water and a non-metal oxide makes an acid. Now remember, nonmetals are to the right-hand side of the zigzag line here. So these are all the nonmetals. So here's an example. Water, again, we'll write that as HOH, and S4 plus O2 minus would crisscross and reduce and become SO2. Right? The 2 would go there and the 4 would go there, and it would initially be S2O4, which would reduce down to S1O2. Now sulfur is clearly a nonmetal. It's to the right of that zigzag line. So we have water and a nonmetal oxide. Now an acid, to put it very simply, is a chemical that when you dissolve it in water releases hydrogen 1 plus ions. So very often we can say that if the formula begins with an H it's likely an acid. So here we have H1 plus, the positive part of the acid, combining with SO3 2- and giving us formula H2SO3. Now once again, whenever we predict the product of a reaction, we couldn't be sure that that's the actual product until we go into the lab and test for it. So this is just a prediction. These are always predictions of what the products would be. All right, number 3 says a metal oxide and carbon dioxide would make a metal carbonate. So here's an example. Calcium oxide. Calcium is this metal here, Ca, it's in the 2+ column. And of course, oxide would be O2-. So calcium oxide would be Ca2+ and O2-. Crisscross that and reduce it, and you get CaO. And for carbon dioxide, remember that we don't write mono on the first word. So when we don't see a prefix on that first word, that means we have one of the chemicals. So that's 1 carbon, and dioxide means 2 oxides. So then the formula is just CO2. Remember that when we're interpreting prefixes like that for a covalent compound, we don't write ions or crisscross or anything. We just directly interpret the prefixes and write those numbers as subscript. So for example, di is 2. All right, so this makes a metal carbonate. The same metal that we're using over here, in this case calcium, is the metal that we're going to use over here in the metal carbonate. So we're using Ca2+. And then for the formula for the carbonate ion, we have to go to the ion sheet, look where the ites and the ates are, and we can see that carbonate's listed right here. It's CO3 2-. So when we crisscross Ca2+ and CO3 2-, we get this formula. All right, so that's it for synthesis. Let's take a look at the next reaction type, which is the opposite of synthesis. It's decomposition. Notice that for Roman numeral 1a, simple synthesis, we have 2 elements forming a compound. For Roman numeral 2a, this is decomposition, that's simple. We have a compound, and this compound would be binary, in other words, made of just 2 elements, breaking up so that on the product side, we have those 2 elements that make up that compound. Let's take a look at a couple examples of simple synthesis. If we have Cu2+ combining with Cl1- to form CuCl2, we would crisscross that, so this 1 goes down here by the Cu and the 2 goes by the Cl. When this decomposes, it will break apart to form Cu, neutral, no charge on that, and Cl in its element form is diatomic. So if you look at the periodic table, you can see that it's shaded in there, so when we put Cl all by itself as an element, it has to be a diatomic Cl2. So the 2 here is from crisscrossing, and the 2 here is because it's a diatomic element. Now this would be called copper 2 chloride. Copper has more than one possible charge. So because we use the 2+ to form that compound, that would be copper 2 chloride. So we could say that copper 2 chloride decomposes to form copper and chlorine. Notice that the compound is neutral, and the elements are always written as neutral elements. Charges are used to crisscross to find the formulas for compounds, but charges shouldn't be written on any species, whether they're compounds or elements, when we have an equation. All right, so here we have Hg2+ with O2-, that's HgO. When you crisscross it, the 2's reduce, and that will decompose to form Hg and O, which is another diatomic element. Remember, oxygen is one of those 7 diatomics, so we have to write it as O2. And again, sometimes these equations are balanced like this one, and sometimes not. This is not a balanced equation. And that's okay. You don't have to have a balanced equation to identify the reaction or predict the product. So the other type of decomposition is the opposite of complicated synthesis. So Roman numeral 1, letter B, is complicated or complex synthesis. And Roman numeral 2, decomposition, letter B, is complicated decomposition. So notice that for synthesis, water and a metal oxide synthesizes to form a metal hydroxide, and for decomposition, a metal hydroxide decomposes to form water and a metal oxide. For synthesis, water and a nonmetal oxide forms an acid, or an acid forms water and a nonmetal oxide. And for synthesis, metal oxide and carbon dioxide forms a metal carbonate, and for decomposition, a metal carbonate forms a metal oxide and carbon dioxide. So these three complicated synthesis reactions are opposite for these first three complicated decomposition reactions. And then there's another one thrown on here. A metal chlorate decomposes to form a metal chloride and oxygen. Let's look at examples of these in more detail. So again, we're just following these recipes. Here's the first one. A metal hydroxide forms water and a metal oxide. So our example is sodium as our metal. It's a 1 plus charge ion, and hydroxide is the OH 1 minus ion, so that gives us NaOH when we crisscross it. Decomposes to form water, and metal oxide would be sodium crisscrossed with oxide. Sodium is a 1 plus ion, oxide is a 2 minus ion. Again, the charges of the ions can very often be determined from their location on the periodic table, like Na in the 1 plus column and O in the 2 minus column, or by looking at the different parts of the reference sheet for polyatomic ions or some other monatomic positive ions. So we get water and sodium oxide, crisscross that 1 and 2 and get that formula when sodium hydroxide decomposes. Our second type of a reaction is where we have an acid decomposing to form water and a nonmetal oxide. Here's an example. H1 plus and SO3 2 minus give us the acid H2SO3. When that decomposes, we get water, HOH, and our nonmetal oxide is going to be a sulfur oxide. We're going to use S4 plus and O2 minus. Crisscross and reduce that, and we get SO2. Number 3, a metal carbonate is going to decompose to form a metal oxide and carbon dioxide. So let's say our metal is Ca2 plus. So our metal carbonate would be a calcium carbonate. Ca2 plus, because Ca is in the 2 plus column there, and carbonate is CO3 2 minus. So the formula for that compound, when we crisscross 2 and 2, they reduce, becomes CaCO3. We're going to form a metal oxide and carbon dioxide. So our metal oxide is going to be calcium 2 plus ion, and oxide is O2 minus ion, crisscrossed and reduced to give us CaO, and then carbon dioxide is CO2. Okay, our fourth type of decomposition is a metal chlorate forming a metal chloride and oxygen when it decomposes. So we're going to use sodium chlorate. We know sodium's in that 1 plus column. We've seen that already. And here's chlorate. Again, it's on your ion sheet. It's mixed in with the other 8s and 9s. ClO3 1 minus. This is one of the halogen oxides. You might want to take a look at that section again. So when we crisscross Na1 plus and ClO3 1 minus, we get NaClO3. And that's going to decompose to form a metal chloride. So we're using the same metal sodium here. And chloride has an IDE ending. So we would find chloride on the periodic table right here, 1 minus, Cl1 minus. So we crisscross Na1 plus and Cl1 minus and get NaCl. And then oxygen is another product. And remember that oxygen is one of the 7 diatomic elements, so you have to automatically put a 2 down at the bottom. And you can see that's not a balanced equation. So that's it for following any recipes that people have discovered. And again, that's just kind of a sampling of different recipes that are out there. There's lots and lots and lots of reactions that people have discovered through the years. Let's take a look at our reference sheet again and move on to Roman numeral number 3. This is double replacement. This is where a compound and a compound forms 2 new compounds. And really, this is like going to a dance and changing dance partners for double replacement. Again, we'll find all of these ions on the ion sheet. Here's our first example. Ba2 plus and Cl1 minus forms BaCl2 when we crisscross and reduce it. Can't really reduce 1 and 2, but I guess when we crisscross it. H1 plus and SO4 2 minus crisscrosses to give H2SO4. And And what we're going to do is change dance partners. Now we're going to take this positive and combine it with that negative. Now we'd never combine positive with positive because like charges repel. So positive and negative from two different compounds, and again positive and negative from two different compounds. Now when we rewrite these new combinations of ions, it's always important to put the positive first, negative second. We always do that. So Ba2 plus and SO4 2 minus crisscross to give us BaSO4. The 2's crisscross and reduce. And then H1 plus and Cl1 minus crisscross with H1 plus written first to give us HCl. That's how all double replacement reactions work, just changing dance partners. Sometimes this is referred to as double displacement, and sometimes metathesis. Metathesis is a Latin term that means transposition. So when you take two things and switch the order of them or change them around, that's transposing. All right, here's another example. We're using iron 2 with sulfide. Crisscrossing the 2 plus and the 2 minus, we get FeS because we crisscross the 2's, drop the charges, and then the 2's reduce to 1's. And HCl is made of H1 plus and Cl1 minus. Now let's trade partners. Fe2 plus and Cl1 minus would crisscross to give us FeCl2. And H1 plus and S2 minus would crisscross to give us H2S. All right, in our last example, Na1 plus and CO3 2 minus crisscross for a formula of Na2CO3, and then Pb2 plus and NO3 1 minus crisscross for a formula of PbNO3 taken twice. Pay attention to that language again. When you pause and say something's taken so many times, that means that that item you're discussing there is in parentheses. So PbNO3 taken twice. That indicates NO3 is in parentheses. All right, so we're going to take the Pb and the CO3, that's the 2 plus and the 2 minus, combine those, crisscross 2 and 2, which reduce down to 1's, and we get PbCO3. And then Na1 plus and NO3 1 minus are going to combine. 1 and 1 are going to give us NaNO3. All right, so that's double replacement. Pretty straightforward. Just change dance partners. Here's our fourth reaction type, single replacement. Single replacement is where we have an element and a compound form a new compound and element. And for single replacement, we always use the activity series. Now, if the element's a metal, it'll try to replace the metal in the compound. That's called metal single replacement. On the other hand, if that element is a nonmetal, it will try to replace the nonmetal in the compound, and that's nonmetal single replacement. Now remember that we always write the element that's a metal first and the element that's a nonmetal second when we write the formula for a compound. Let's take a look at some single replacement reactions and how to use the activity series. We only use the activity series for single replacement reactions. That's an important point. Don't start using that for all other reactions, only for single replacement. This is sometimes referred to as single displacement too. Let's look at metal single replacement examples first. So let's say that the element, right, we have an element and a compound as reactants. Let's say the element is zinc. Zinc is a metal. It's on the left-hand side of that zigzag line there. That's a metal, Zn. And that's combining with the compound copper 2 sulfate made of Cu2 plus crisscrossed with SO4 2 minus. The 2 and the 2 crisscross and then reduce. So what we're going to do is find out if zinc is chemically active enough to kick the copper out of the compound. So if we take that ion sheet and flip it over, we can see the metal activity series right here. Now this is a representative list of metals. It's not all inclusive, but it has a lot of common metals on it. You will notice that we're trying to compare zinc and copper. So zinc is right here, Zn, and copper is right here, Cu. Notice that zinc is higher up on the list than copper. And this is a vertical list on purpose. The metals that are highest up on the list are most chemically active. They most easily give away their electrons and form compounds. form positive ions, and that means they would be in compounds. And metals that are at the bottom of the list are less chemically active. They don't give their electrons away as easily. So we have Cu and Fe. Notice that Fe is above Cu, so it's more chemically active. What that means is the Fe, oh, I'm sorry, we're comparing Zn. Zn and Cu. Zn is above Cu. And because Zn is above Cu, it's more chemically active when it's higher up on the list. The Zn will kick the Cu out of the compound, and when the Cu leaves the compound, even though it's a 2+ ion in the compound, when it's all by itself, it forms a neutral Cu atom. And now zinc, which was a neutral atom when it was all by itself, on the left-hand side of the arrow, is going to form a 2+ ion and combine with SO4 2- to form ZnSO4. Well, how do we know that zinc's going to form a 2+ ion? Well, the answer is not by looking on the periodic table. We can't predict its charge when it's a transition metal. But through experimentation, and because it's written on this reference sheet, we know that zinc forms a 2+ charge. So when an element is higher up than the element is trying to replace, it will replace it. Zinc is a metal, so it's going to try to replace the metal. The first element in the compound is always the metal. When it does so, we crisscross Zn2+ and SO4 2- and get ZnSO4, and the element that gets kicked out of the compound always becomes a neutral element. Now what if we were trying to do that in reverse and have copper combine with zinc sulfate? Now remember that copper is lower than zinc on the activity series. That means it's not chemically active enough to kick the zinc out of the compound. So there will be no reaction, or NR. Now what if we have non-metal single replacement? What if the element is a non-metal? Right? Here we had a metal. What if we have a non-metal? That would be an element to the right-hand side of that zigzag line, like Br. Now Br happens to be a diatomic element, so it would be Br2 in its element form. Remember, those 7 shaded in elements automatically form a 2-atom molecule when they're elements. So the Br, being a nonmetal, will try to replace the nonmetal in the compound. The nonmetal is always the second element in the compound, the element to the right. We always write metals first, then nonmetals second. So will Br be active enough to kick out the I? For this, we have to look at the much shorter nonmetal activity series. There's 2 reasons this is a shorter list, and one, I guess it's kind of not much of a reason, but we don't have too much space here before we're out of paper. But more importantly, there aren't that many nonmetals compared to the metals. And notice we don't even have the inner transition metals identified on here. There are many, many more metals than nonmetals. So of course we're going to have a shorter list for nonmetals. Notice that on this nonmetal activity series, Br is just above I. That means Br is more chemically active. So the Br will kick out the iodine from the compound. It'll combine with Na1+, which is the positive part of the compound. And when Br forms an ion, it's in the 1- column. And the iodine that was a 1- in the compound on the left is going to be kicked out of the compound as a neutral iodine atom. Iodine is also one of the 7 diatomic elements, so we have to put a 2 because it's one of those 7 shaded in elements. These 6 and hydrogen are automatically going to get a 2 like this when they're in their element form. Now you might say, well, what about the iodine there? It doesn't have a 2. That's right, because it's not an element, it's in the compound. When elements are in compounds, we crisscross and reduce to find their formula, or if it's a covalent compound, we interpret prefixes. Now you can see this is not a balanced equation, but that's it for that equation. What if we tried to do that one in reverse? Had the iodine combining with sodium bromide, where the iodine nonmetal would try to kick out the bromine, that's also a nonmetal. Well, again, if we go to the activity series, we can see that iodine is below bromine. Because it's not above that chemical, it can't kick it out, and this would be no reaction, represented with Nr. So we've saved the easiest for last. Our last reaction type is combustion. Combustion is just what it sounds like. It's burning. It's where we take a hydrocarbon or a fuel, that would be a carbon chain or some type of a carbon-hydrogen combination, combine it with an excess of oxygen, and get carbon dioxide and water. Now, if we don't have an excess of oxygen, for example, if we're just burning a candle in the air, and the air is slightly under 1/3 oxygen, there's not enough oxygen to completely burn all of the wax, that's the hydrocarbon in the candle. So we get some carbon monoxide, some black carbon soot that comes up as smoke and kind of dust that comes off the candle flame, as well as carbon dioxide and water. So when we have some carbon monoxide, some carbon dioxide, and water, we call that incomplete combustion. And that's because of a lack of oxygen. Well, we typically don't want to burn like that. We want to burn hotter flames, that would be not yellow but blue flames, and cleaner flames that would only produce carbon dioxide and water, no carbon soot, no carbon monoxide. So we're going to assume that we always have an abundance of oxygen and that the only two products we get are these two. That's called complete combustion. And when you see a flame like that, that would be a blue flame, a nice hot blue flame. So here's some examples. CH4, that's a hydrocarbon, or C2H5OH. Notice that there's some oxygen mixed in with that hydrocarbon, and that's fine. That's called an oxygenated fuel when we have that. And then C6H12O6, and you might recognize that. That's glucose. That's the fuel that's going through your circulatory system, through your veins and arteries to carry energy to your cells. Now, whenever we combine a hydrocarbon with oxygen, and you know, sometimes there's oxygen in the hydrocarbon, sometimes not, but when we combine it with an external O2 source, typically the air, we get carbon dioxide and water. Let's take a look at some different combustion possibilities. Notice that whenever we combine these hydrocarbons and oxygens, we're getting carbon dioxide and water. So combustion is actually very easy to predict, and the only thing you really have to be careful about is do not mistake these for single replacement reactions, because it kind of looks like we have a compound and an element where you would want to do a single replacement. But when we very specifically have some type of a hydrocarbon and oxygen, and a hydrocarbon again is like some kind of a carbon chain or a big longer carbon compound with some hydrogens attached and maybe some oxygens attached too. They burn as fuel. All right, so if we look at these 5 reaction types, kind of summarize these, we can see there's pretty much a different set of reactants for every reaction type except for these two where we have a star. So for synthesis, we can have 2 elements forming a compound or 2 compounds forming a compound. And we can follow those 3 recipes that are on that reference sheet if we have a complex synthesis. For decomposition, a compound that's made of 2 elements would break up into those 2 elements, or a compound that's made of more than 2 elements would break up into 2 compounds, forming, or following rather, the 4 recipes that are on this reference sheet. Now again, if you were to do some problems that go beyond the scope of this course, beyond that reference sheet, you could look up reactions in a larger reference manual or in a reference database. But typically, we stick with reactions where we can just use this sheet. All right, for double replacement reactions, we have 2 compounds combining to form 2 new compounds, and this is where we change dance partners. So the positive from this compound combines with the negative from that compound, and the positive from that compound combines with the negative from that compound, so we get 2 new compounds. In single replacement, we use the activity series, and we see if the element is active enough to kick out the like element in the compound. So if the element's a metal element, it's going to try to replace the metal in the compound. The first element's the metal. And if the element is a non-metal, it's going to try to replace the non-metal in the compound. And in a compound formula, the second element is the non-metal. If the element is not higher up on the activity series list, then we'll get a no reaction as a result. And then finally we have combustion reactions, where some type of a hydrocarbon, CXHY, and maybe some O in there too, and the O doesn't have to come at the end, it could come anywhere in the formula, combines with O2, we get carbon dioxide and water. And we'll always assume that we have complete combustion, meaning we have an abundance of oxygen. So what about these two stars? What about double replacement, where we have two compounds on the left, and complex synthesis, where we also have two compounds on the left? How would you determine whether we're going to do this reaction when we have two compounds, or this reaction when we have two compounds as reactants? Well, the answer to that is, let's keep an eye out for water and CO2, very commonly known, recognizable compounds. If you see that either one of these is water or carbon dioxide, you know we have a simple synthesis. In fact, it's not a bad idea on the reference sheet to circle water, water, and carbon dioxide to remind yourself that we're kind of keeping an eye out for those, so that if we see those in reactions where we have two compounds on the left of the arrow, we know we have a complex synthesis. And if we don't see water or carbon dioxide, we know we have a double replacement. All right, so if you understood what we went through in this video, you should be able to identify the reaction types using these abbreviations: SYN for synthesis, DEC for decomposition, DR for double replacement, SR for single replacement, and COM for combustion. You should be able to identify the reaction type for all 10 of these chemical reactions. Good luck.